Hey there, folks. So in this video, we're going to look at a particular nested sequence of square roots. That would be this expression right here. And the question is what it converges to and whether we can control what it converges to for a careful choice of A. A, by the way, is some as yet unspecified but positive real number here. So for A greater than 0, we consider the expression, the infinite nested sequence of square roots that I've written above, square root of a plus square root of a plus the square root of a, etc., 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 on for infinity. So before even attempting to work with it, one should address the question of convergence. I'm not going to do so in this video, although I could, so I'll just make a brief remark about convergence. It can be shown that this expression converges, and showing that, and you can do so by way of the monotone convergence theorem. Sometimes abbreviated MCT. Now, like I said, I'm not going to do so here. It entails showing two things. For one, that the sequence is bounded, and secondly, that it's monotone, monotone increasing as in fact happens to be the case. So it's possible to show that this is increasing and bounded above, hence that it does converge. For the purpose of this video, I would just ask you to take my word that that's the case. So we will assume this to be the case. That said, or with that point aside, let me give a name to this limit. So let the limit of the expression be called L. Okay. So L is equal to this infinite sequence of nested square roots. And you'll notice that actually L depends on A, or at least in theory, it could depend on A. In fact, it does depend on A. So technically, I should probably, I don't know, put like a subscript A. But I'm not going to do that. I'm just going to ask you to keep in mind that L depends on A. Well, let's see how L depends on A. So let's compute the limit. Note that L is contained in the expression for L. There's another copy of L right there. Here, where's my pen? Look at this. That's L right there. So note that we have that L is equal to the square root of A plus L again. So what? So L squared is equal to A plus L, i.e. L squared minus L minus A equals 0. We can solve this by way of the quadratic formula, of course. And that gives that L is equal to, what is it? 1 plus or minus the square root of 1 plus 4a all over 2. But with a little thought, we can see that the minus actually doesn't make sense. Why is that? Look at this expression. A is positive. A has to be positive, by the way, for these square roots to make sense. So we've got the square root of a bunch of positive expressions, hence we would expect a positive result. This is clearly negative when we use the negative sign here. So we're going to disregard the negative and keep the positive. Note that it's clearly positive when we use the positive sign. Okay, so disregarding the negative sign, we have that L, oops, here, let's just copy and paste this. L is equal to 1 plus the square root of 1 plus 4a all over 2. Okay, good. So, we have an expression for the limit. Let's see, one thing to point out about this limit, with a being positive, remember, we said from the start that a is a positive real number. We can see that L is always going to be greater than what we would get if we replaced a by 0. Replacing a by 0 gives that L equals 1 plus 1 over 2, which is 1. So note that L is always bigger than 1. So I actually found some information already about the question that I initially asked. It can't converge to any positive number. If it converges, it'll converge to a number that's bigger than 1. So that we already have some information about the type of limits that we're going to get. How about we solve this expression for a in terms of L? So note that. Okay. So apparently, let's just do some arithmetic here. 2L minus 1 equals the square root of 1 plus 4a. So 2L minus 1 quantity squared minus 1 equals 4a, i.e. a is equal to 1/4 of, now I can factor this as 2L minus 2 and 2L. And we can actually cancel a factor of 4 to get L times L minus 1. Okay. So we figured out what A is in terms of L. Now let's try, now that we have A in terms of L, let's consider a few special cases. In fact, before I start choosing what the limit L is, what about the case that say A is equal to 1? So first, if A equals 1, we find that the square root of 1 plus the square root of 1 plus the square root of 1, etc. Well, according to this formula for the limit, if I just replace a with 1, I get that this is equal to, here, let's just, well, you can see what we get here if we replace a with 1. We get 1 plus the square root of 5 over 2. That should be familiar. This is the golden ratio. You may have heard of it. Sometimes it's notated with a phi. But now, how about instead of choosing values of A, let's choose some values of L. So that was one special case. I'm just doing a few sort of special, interesting cases. So now, how about let's see, what do you want this limit to equal? Do you want it to equal 2? How about 2? So if we consider the case that the limit is 2, then A, which is L times L minus 1, is 2 times 1. So what? So 2 is equal to the square root of 2 plus the square root of 2 plus the square root of 2 plus etc. So that's kind of neat. 2 is the square root of 2 plus the square root of 2 plus the square root of 2, yada, yada, yada. Okay, so that's kind of a pretty looking case. I don't know, you want to try 3? How about if L is equal to 3? Well, then what do we get? Then A is 3 times 2. So A is equal to 3 times 2, which is 6. So apparently 3 is equal to the square root of 6 plus the square root of 6 plus the square root of 6 plus etc. That's kind of a neat and pretty result. What else? What other special cases should we do? We did 2, we did 3. I don't know. You want to see 4? Why not? Let's just do while we're doing these nice easy numbers. Let's try L equals 4. In that case, let's see what A is 4 times 3, which is 12. So apparently 4 is equal to the square root of 12 plus the square root of 12 plus the square root of 12 plus etc. Dang it. All right, so that's kind of cool. Notice that our limit doesn't have to be an integer. It just has to be some real number bigger than 1. By the way, you'll notice this formula doesn't make sense if L is 1 or less than 1. So it only makes sense for numbers that are bigger than 1 in accordance with what we noticed about this expression for L, right? It has to be bigger than 1. I don't know, how about 3/2? Okay, so let's see. If L is equal to 3/2, then A is equal to 3/2 times 1/2, or 3/4. So what do we get? We get that 3/2 is the square root of 3/4 plus the square root of 3/4 plus, you probably get the idea. Do you think I need to do 3 of these square roots every time I write this expression, or would just 2 of them suffice? 2 of them would probably suffice at this point, or even just 1. So anyway, that's a pretty cool looking limit. I could do other rational numbers. I could do irrational numbers. I don't know. How about like pi? Let's do pi. So how about if L is equal to pi? Well, then what do we get for A? A is apparently pi times pi minus 1, or if you want, you could write that as pi squared minus pi. So what? So apparently pi is the square root of pi squared minus pi plus the square root of pi squared minus pi plus the square root of pi squared minus pi plus etc. So that's kind of interesting. Yeah, it looks pretty cool. And I could do this with, if I say replaced all the pi's with e's, I would get a similar expression. So if L is equal to e, then A is e times e minus 1, which is e squared minus e. So e is e squared minus e plus square root of yada, 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 yada. That's kind of cool. I could do this with, say, root 2 if I replaced all the e's with root 2's. But I think you get the idea. And I don't know, no other sort of particularly interesting cases come to mind. So I think I will leave it at this, and thank you for watching.